and I've arranged them in 10 columns. And you can see I've coloured in the prime numbers. Hopefully you can spot those. So my definition of a prime number would be a positive integer, positive whole number, bigger than 1, whose only factors are 1 and itself. So it's divisible exactly by 1 and by itself, but not by anything else. And by convention, we don't include 1 as a prime number. It just turns out to be more convenient not to. And I'm sort of hoping that as I'm talking and reminding you of prime numbers, and I'm sure you all know about prime numbers already, I sort of hope that you're noticing patterns from the way that they're arranged on the grid here, because that's why I like putting them in the 10 columns and highlighting the primes here, is that we start to notice patterns. And actually, there are quite a lot of patterns that we might notice. Let me give you an example of the kind of thing I mean. If you have a look at the columns starting 4 and 6 and 8 and 10, on the basis of this data, those columns seem not to contain any prime numbers. And when you stop and think about it a bit, those numbers in those columns are all even numbers. And if you're an even number, it's really hard for you to be prime, right? So any even number bigger than 2 will be divisible by itself and by 1 and by 2, so isn't prime. So 2 is the only even prime number. And that shows that no matter how far down those columns we went, the 4, 6, 8, and 10 columns, we'd never find any prime numbers. So that's not the most difficult example of a pattern amongst prime numbers, but hopefully that gives you an idea of the flavor. And in particular, I'm looking at the information here to get ideas, to get inspiration for what patterns I think there might be. I can see what I notice. I can make predictions. I can make conjectures, we call them in maths. But then as a mathematician, what we want to know is what would happen if there were more rows on the slide? Would that same pattern continue further down the column? That's kind of what we're interested in. So 2 is the only even prime. So in fact, in its column, the only prime will be 2. And you can think about why 5 is the only prime in its column. But actually, there are quite a lot of primes in the 3 columns. So there's something different about 2 and 5 compared, for example, with 3 and 7. So there's something to think about there. And as I said, there are lots of patterns to explore here, and I'm not going to try to talk about all of them today. But maybe if you are inspired, you can keep thinking about it after the talk. One thing I think it's good to think about is how many prime numbers there are, because there are 2 very different possible scenarios here. So here we've got the numbers up to 100. But if we kept going with more and more rows on the slide, would we eventually run out of prime numbers? Would we reach the largest prime number and then meet no new prime numbers? Or can we keep meeting new prime numbers? Are there infinitely many prime numbers, or is there a largest prime number? That feels like quite an important question. It also feels like a question it's really hard to guess an answer to looking at this data. I mean, there are some primes up to 100. There are 25 primes up to 100. But it's quite hard to tell looking at the grid whether there might be a largest prime. It does feel like they're getting more spread out towards the bottom. I mean, at the top, they're bunched up close with 2, 3, 5, 7. Near the bottom, they're spread out 83 to 89, big gap to 97. And I think it feels plausible that for large numbers, we'd expect there to be fewer primes, because if you're a really big number, it's hard for you to be prime because there are lots of potential factors. There are lots of smaller numbers that might divide our large number. It's quite easy for 7 to be prime. There aren't many smaller numbers that could go into it. For a really big number, it's quite hard for it to be prime. So we expect the primes to get kind of more spread out, but I don't know how to turn that intuition into a guess of there is a biggest prime or there isn't a biggest prime. I guess we could ask a computer to go away and think of the largest prime it can. So, you know, I'm giving this talk on my laptop. I can ask my laptop to go away and compute prime numbers, and Maybe it comes back after a fortnight and says, this is the largest prime I've thought of, but that tells us nothing, right? Because maybe the computer has thought of the largest prime in the world, or maybe if I'd given it 4 weeks instead of 2, it would have thought of a larger prime. So we need maths. And this is a really old question. Is there a largest prime number? So mathematicians have known the answer to this question for more than 2,000 years, which I think is extraordinary. And it's a theorem, a fact that we can prove that there are infinitely many prime numbers. There is no largest prime number. So I'm not sure whether you're familiar with this fact already, whether this might be a new fact for you. I thought I'd share with you my favorite proof. There are lots of lovely proofs that there are infinitely many prime numbers. I thought I'd share with you a proof now. And maybe this will be new for some of you. If it's not new, hopefully you like it as much as I do and will be happy to see it again. I think this is a very beautiful proof. If it is new to you, don't worry if you don't take in all the details. I'm not going to test you on it later or anything like that. So this is a proof that we find in the work of Euclid. And it goes something like this. I think of it as a thought experiment. So secretly, we think there are infinitely many prime numbers. There's no largest prime number. Let's imagine for a minute that we're in a parallel universe where there is a largest prime number. And the plan is to kind of explore the consequences if there is a largest prime number, and we'll show we reach an impossibility. And so there can't be a largest prime, and there must be infinitely many primes. That's the kind of idea. So let's do this thought experiment. Let's imagine that there is a largest prime. And then I can take a very large piece of paper and on it write all the primes in the world, 2, 3, 5, 7, 11, 13, and so on, all the way up to whatever the largest prime is. So my piece of paper has all the primes in the world. And here's Euclid's gorgeous idea. Euclid says, multiply all the primes together and add 1. So I take all the primes on my piece of paper, multiply them all together, and add 1. That's going to be some enormous number. Who knows what it is? It doesn't matter. It's a thought experiment. One thing we can say for sure about this very large number is that it must have a prime factor, because every positive whole number bigger than 1 has a prime factor. It's prime itself, or it's divisible by a smaller prime. So this very large number must have a prime factor. And we've got a list on our piece of paper of all of the primes in the world, so we can check which of them divide this very large number. So the first prime on the list is 2. Does 2 divide this very large number? No, because the number is 2 times some stuff plus 1. It leaves a remainder 1 when we divide by 2. Next prime is 3. Does 3 divide this very large number? No, because this number is 3 times some stuff plus 1. It leaves a remainder 1 when we divide by 3. Does 5 divide this number? What Euclid has done is take all the primes in the world and from them build a number that isn't divisible by any of them. And now we feel slightly sick because this number must have a prime factor. It must be divisible by a prime, but also we've got a complete list of all of the primes in the world, and this number isn't divisible by any of them. And the mathematical way of saying now we feel slightly sick is it's a contradiction. It's an impossibility, an absurdity. So what does that mean? It means that our original assumption must be incorrect. And so there must be infinitely many primes. It's not possible to write a complete list of primes. So this little square box at the end, maybe you've seen this symbol for the end of a proof in mathematics. So that is Euclid's proof that there is no largest prime number. There are infinitely many primes. And the first time I saw this, the first several times I saw this, it took me a while to get my head around it. This kind of style of contradiction argument takes a bit of getting used to and so on. But I think when you've got your head around it, I think it's a really beautiful argument, because when you think about it, we're proving something really hard here. And yet with this kind of elegant idea, I can fit the whole proof onto one slide. It's kind of such a clever idea. Also, I'm really happy that there are infinitely many prime numbers, because I feel like the world is a more interesting place with infinitely many primes. So let me go back to my grid with the primes highlighted, safe in the knowledge that no matter how far down these columns go, we will keep finding new prime numbers. And I feel like I need to confess, because I feel like I've slightly misled you. Because I talked about the primes being more bunched up early on, 2, 3, 5, 7, and then they're getting more spread out later on, 83, 89, 97, they're getting more spread out. It feels plausible they're getting more spread out, but let me show you what happens if I put another row on the slide. Because 101, 103, 107, 109, they are all prime numbers, bunched up, close together again. And this, for me, captures one of the things I love about prime numbers, which is every time I think I understand what's going on, it's a bit more subtle than that. There's always more to explore. So it is true that on average, the primes get more spread out. And that intuition about it being hard for a large number to be prime, that's correct. On average, they get more spread out. But the on average is really important, because it seems like we keep finding these clusters of prime numbers bunched up close together. And I want to focus now on prime numbers that differ just by 2, like 3 and 5, 17 and 19, 59 and 61, 101 and 103. There are lots of examples on this grid of pairs of primes that differ by 2. And we know, thanks to Euclid, that there are infinitely many prime numbers. So it seems to me really natural to wonder, are there infinitely many pairs of primes that differ by 2? These primes that are kind of really good friends, they're really close together. And I don't know the answer to that question. So this is called the twin primes conjecture, and it must be one of the most famous unsolved problems in mathematics. So the prediction, the conjecture, is that there are infinitely many pairs of primes that differ by 2. And there are good reasons to think the conjecture should be true. There are good reasons why we might make this prediction, but we don't know how to prove it. And as mathematicians, we're in the business of proof. I think it's intriguing that a statement like this, which is not so hard to understand, you don't have to know lots of very advanced maths to understand this problem, we still don't know the answer to. I think that's fascinating. But there has been some recent progress in the last few years on the twin primes conjecture. And I thought I'd tell you a little bit about that now as a kind of insight into some of the ways that mathematical research can happen, I guess. So the recent progress is using some quite sophisticated mathematics. Let's start by trying to prove the twin primes conjecture ourselves, because why not? It's good to be ambitious. And I've got an idea for proving the twin primes conjecture, using that idea from Euclid's proof I showed you just now, that there are infinitely many primes. So Euclid's proof was take all the primes in the world, multiply them together, and add 1. In Euclid's argument, we could instead multiply together all the primes in the world and subtract 1. And the argument will work out just the same. From Euclid's point of view, it doesn't matter whether we add 1 or subtract 1. And the thing is, if you add 1 to a number and also subtract 1 from that number, you end up with 2 numbers that differ by 2, and maybe they could be twin primes. Let me show you what I mean. So if we took 2, 3, and 5 as our prime numbers and multiply them together, let's see, 2 times 3 times 5, that's 30. Add 1, subtract 1, and we get 29 and 31. And that's a pair of twin primes. It's good, right? So we could just kind of keep doing that, and maybe that would give us infinitely many pairs of twin primes. Let's do another example. So if we had primes 2, 3, 5, 7, multiply those all together, that's 210. add 1, subtract 1, we get 209 and 211. And then there's this kind of crushing disappointment as we discover that 209 is not a prime number. 209 is 11 times 19. This process does not always give us a pair of twin primes. We have not proved the twin primes conjecture, sadly. What we have done maybe, though, is just understand Euclid's argument a little bit better, because I think it can be tempting to think that Euclid's process of multiply these numbers together and add 1 is guaranteed to give us a new prime. It's not guaranteed to give us a new prime. It is guaranteed to give us a number that's not divisible by any of the primes on our original list. And with 29, 31, for example, that might be a new prime. But as with 209, 209 is divisible by 11 and 19. Those are new primes that weren't on our original list. So, okay, we haven't proved the twin primes conjecture. That's not so surprising. I did tell you it was one of the most famous unsolved problems in maths. Maybe that helps a little bit with an insight into Euclid's argument. My experience as a mathematician is that I spend a lot of time failing to prove things. That's perfectly natural. Maths problems are hard. It's a challenge. We have to try to solve them. But even if we don't solve a problem, we can still learn something from it. My teenage years, I failed to solve, if you like, a lot of maths Olympiad problems. I spent a lot of time thinking about problems. I solved some of them. I did not solve a whole lot more, but I could still learn something useful from trying to solve the problems, even when I didn't manage to solve them. Let me tell you more about this recent progress on the twin primes conjecture. So this goes back to May 2013, so a few years ago now. And there was this kind of exciting announcement that got everybody in the mathematical community kind of go, oh, what's going on? A mathematician called Yitang Zhang made this announcement. He was not a famous expert in the area. He's originally from China. He was working in the US. He hadn't always had a job as a professional mathematician. It had been hard for him to get a job. At this point, he was working in a university, but this kind of came out of the blue. It's a really extraordinary achievement. And Yitang Zhang announced that he was able to show that there are infinitely many pairs of primes that differ by at most 70 million. So infinitely many pairs of primes where the gap between the primes is less than or equal to 70 million. You might be thinking, but hang on a minute, the twin primes conjecture is about pairs of primes that differ by 2, and 70 million is like massive compared with 2. And I agree. What's exciting about this result is it's the first time anybody had managed to prove a result of this type. And while 70 million is a lot bigger than 2, it's much smaller than infinity, which is kind of where we were before. So lots of people were very excited, especially because what Zhang did was he'd read the recent work of experts in the field, the previous progress on the problem. He'd understood it really well. And he kind of managed to push their techniques beyond even what the apparent experts thought was possible. So it's extraordinary insight and perseverance managed to prove this. And then mathematicians started looking at Zhang's work and checking, do we believe it? But also, what's so special about 70 million? Could we make 70 million a bit smaller? Could we get closer to the twin primes conjecture? And there was a good example of this only a few weeks later, the end of May 2013. A mathematician called Scott Morrison in Australia put on his blog a post called, I just can't resist. There are infinitely many pairs of primes that at most 59,470,640 apart. And that blog post title kind of encapsulates something that Scott Morrison noticed and other people were noticing, that there was this kind of opportunity to be the world record holder on one of the most famous unsolved problems in mathematics. Because by tweaking what Zhang had done a little bit, Scott Morrison was able to improve on that 70 million. and other people started doing similarly. Zhang didn't work to make that 70 million as small as he possibly could. He prioritized clarity in his argument. He prioritized publishing his work quickly so that nobody else beat him to it, I guess. But other people were going, oh, well, maybe. And because Scott Morrison put this on his blog, other people could come along in the comments and post their ideas too. And this got kind of formalized and organized a little bit in something called the Polymath Project. These are started a few years earlier by a mathematician called Tim Gowers on his blog. Polymath is kind of Tim Gowers' attempt to answer the question, is massively collaborative mathematics possible? Is it possible for lots of people to come together and work together on a problem and solve it? Maybe they wouldn't have been able to solve it individually, but by working together, they could solve it using the internet to facilitate that. So just a short while after Zhang's work came out, and then Scott Morrison, another mathematician called Terry Tao, suggested having a polymath project on it called Polymath 8, and it's called Bounded Gaps Between Primes. And this is all still online. So you can Google for Polymath Bounded Gaps Between Primes. You can search online for it. I've put the two aims here of the project because the first aim was kind of improve on 70 million. Can we make that closer to 2 for the twin primes conjecture? The second goal was to understand what Zhang had done, to see whether it could be made simpler in any way, and to understand how it built on previous work of these other mathematicians who'd been working in the area. What was Zhang's new ideas? How was it different from what had been done before? And so through the summer of 2013, mathematicians worked on this on Polymath. I've got some screenshots here of the kind of league table of showing the progress. So the crucial column is the one-headed H. And you can see there's a row there for May and 70 million with Zhang. And then later rows, people would come along and say, well, I think I can get this number. Here's a link to my blog or the website where I've posted the details. And then other people can come along and check. And again, it's all in public. This is one of the things that's so remarkable about Polymath, is that it's a completely public collaboration. It's not one mathematician working with their particular colleagues. Anybody who wants to can join in, which is really new. And this continued. I don't know whether you can see on this screenshot, some of these numbers have been crossed out. That's because they built on a draft paper by a mathematician who is an expert in this area, but it turned out there was a small mistake in the paper. So these numbers got crossed out. This is one of the things I think is really interesting about Polymath. The process of solving a mathematics problem is not a direct one. You don't look at the problem, think, oh, I know how to solve that, and then write down a solution. Or if you do, then the problem was too easy. The interesting problems, maybe you have this experience when you're trying Olympiad type problems. This is the kind of challenge I enjoy, where you look at a problem and you're not quite sure which techniques you might use, what strategies to use. And so you try things and they don't work, and you try more things and they don't work out. And eventually you try something and it does. And with Polymath, you see that whole process. This is how professional mathematicians work. We try out ideas. Sometimes they work, sometimes they don't. We learn from the ones that don't. We learn from the ones that do. So through the summer of 2013, this number keeps dropping and dropping in this column for H. Fantastic progress. This progress would have happened without Polymath, but Polymath was a very efficient way to bring together lots of people who were interested, made it, I guess, more streamlined for the collaboration. So by August 2013, Polymath have managed to show that there are infinitely many pairs of primes that differ by at most 4,680. Now, that is still a way off from 2, but it's a lot better than 70 million, right? This is brilliant progress. And then Polymath kind of got stuck, basically. Progress dried up a little bit. This is what happens sometimes. So the people involved with Polymath went to write up their paper for publication. Even though it was all online, they still needed to write down the arguments carefully, check all the details, send it off to be checked by experts to be published. And everybody kind of thinks, what next? When will the next breakthrough come? And as it happens, the next breakthrough was quite soon afterwards, in the autumn of 2013, kind of October, November time. And a mathematician called James Maynard came along. He's actually one of my colleagues in Oxford. At the time, he'd just finished his PhD. He was working in Montreal in Canada. He's now back in Oxford. He did his PhD in Oxford as well. And James Maynard managed to show that there are infinitely many pairs of primes that differ by at most 600. So a big step forwards from 4,680, getting even closer to the twin primes conjecture, and also in some ways simplifying the argument, having some new ideas that made the argument a bit easier. Terence Tao had some similar ideas at the same time, but James Maynard got a slightly better numerical bound. So then polymath wake up and say, well, this is fantastic, because building on the work of Zhang, building on the work of those previous mathematicians, we managed to show there were infinitely many primes that differ by at most 4,680. Now, James Maynard and Terence Tao, they've got these new ideas. They've got down to 600. Can we go even further? And so the polymath project kind of woke up again and kept going. And by April 2014, polymath had managed to show that there are infinitely many pairs of primes that differ by at most 246. So again, another really great step. To the best of my knowledge, that is the state of the art. So this is a few years ago now. About this time, I started to think maybe it would be a good idea to write a book about this. That was a kind of nerve-wracking experience. If somebody had proved the twin primes conjecture while I was writing my book, I'd have had to do some quick rewriting. They haven't proved the twin primes conjecture yet. There has been progress in various ways, assuming that we knew the answer to some other problem, that we could improve on 246. People have taken this kind of ideas that went into this argument and applied them in other kind of situations. So where next? Well, I believe the twin primes conjecture is true. There are good reasons to think that. I believe that as mathematicians, we will prove it. I have no idea when. So it might be next week or next year that somebody announces it. It might be in 10 or 20 years' time when one of you attending the talk today has studied mathematics further and specialized in this area, and maybe will have found a solution. So I don't know when we will prove the twin primes conjecture, but I'm looking forward to finding out. I think this is a good time for me to stop talking. So let me leave you with a problem for you to think about. So 3, 5, and 7, I think of them as like two pairs of twin primes glued together in the middle. 3 and 5 are twin primes, 5 and 7 are twin primes. So let's call that a prime triple, where we've got these 3 evenly spaced primes where the gap is 2. So this is a warm-up problem for you. The twin primes conjecture is quite hard. This is a more approachable problem. So the problem for you to think about is, are there any more of these prime triples? So I will let you think about that. And I'm going to stop talking and see whether you have any questions you'd like to ask me. And thank you very much for listening to me. Let me stop sharing my slides and then I can see you all. I can always share slides again later if that's helpful. But yeah, if you've got questions, please fire away. Now everyone's going to be shy.
Excuse me, I have a question.
Go for it.
What kind of subject do you view maths as?
What kind of subject? Sorry, I didn't hear.
What kind of subject do you view mathematics as?
So my particular kind of branches of mathematics that I'm interested in are number theory and combinatorics. So those are kind of things that I enjoy. And I guess you might have done a little bit of some of those things already. And then one of the things I like about number theory and combinatorics is that we start learning these ideas when we're quite little at school. And yet, as with the twin primes conjecture, there could be these kind of unsolved research problems. In terms of my teaching, I teach undergraduates from different subjects in pure maths, kind of theoretical maths. So I teach group theory and linear algebra and analysis and those kind of things. I'm not sure how many of those you would have studied already. So I hope that answers your question. And I should say, I've got the chat open. So if you're more comfortable typing, I'm very happy to try to answer questions that I spot in the chat. Or as far as I'm concerned, you're very welcome to turn your microphone on and ask me a question that way if you prefer, whatever you find most convenient.
When did you realize you were interested in maths?
Oh, thanks for asking. I always enjoyed maths. When I was quite little, I enjoyed maths. I find it kind of interesting that I've kept being as excited about maths, even as my understanding of what maths is about has changed. And I guess when I was 6 or 7 at school, I kind of liked doing my sums. Maths then, as I got through school, as I started doing Olympiad maths, I just sort of discovered I really enjoyed the problem solving, that thing of being presented with a problem and not knowing what techniques to use. And I sort of discovered number theory when I was about 17. I came across a really good book that got me excited about number theory, as well as some of the camps I was going to and learning about it. So yeah, for me, I've always really enjoyed maths. I know some of the students I teach, so they come to Oxford usually when they are about 18, something like that, about 18 years old. Some of them have always loved maths. Some of them have only decided maybe a year earlier that they wanted to specialize in maths. They found it hard to choose what else to do. Okay, I've got some questions coming in the chat as well. So I will pick these up, but do jump in on the mic, on your microphone if you'd like to. So someone's asked about my favorite subject except maths. I'm interested in all sorts of things. I was really happy to specialize just doing maths when I got to university. But the 2 years before that, in England, we call it sixth form college, where I went to do my A-levels. I did maths, more maths, physics, and I also studied languages. I really enjoyed studying languages. I think there's something about linguistics and mathematical brain. It's a sort of similar kind of, I like pattern and structure and those kind of things, I guess. But I also really enjoyed music. I spent a lot of time as a teenager playing in orchestras. So yeah, lots of different things. I'm just pausing to have a drink and to see whether anyone wants to ask me anything on a microphone, and then I will go back to questions in the chat.
Hello.
Hi, go for it.
I wanted to ask that, what is your view regarding maths in our real life?
Yeah, so maths in real life. I confess the maths I do is not motivated by real life, but I'm really happy that I work with colleagues who work in applied mathematics, using mathematics to help society in lots of ways. I'm really happy that some of my students go on and use the kind of things that I've taught them for the benefit of society in other ways. And I feel like, I don't know what it's been like in Nepal. In the UK, we've heard a lot more about maths in the press, in the newspapers and on TV in the last 18 months because of the pandemic, because some of my mathematical colleagues have been doing such important work with modeling how the disease is spreading, with trying to advise government on, do we need to lock down? Do we need to restrict people's behavior in some ways to keep people safe? Those kind of things. And I think that's maybe highlighted to a wider audience in the UK how maths benefits society really directly. Those of us who do maths know that maths underpins our lives in lots of ways. And I have colleagues whose work is helping to tackle climate change. I have colleagues whose work is important for keeping our financial systems going, for software development and data analysis in all sorts of settings. So I think it's fantastic that maths can be used in so many ways. One of the things I love about maths is its diversity, that you can be interested in maths for lots of reasons. You can specialize in lots of different bits of maths. So my students all have to learn some linear algebra, but then they might use their linear algebra to help with understanding number theory. They might use their linear algebra to help with improving healthcare, to help with tackling climate change, lots of different things. I find it fascinating that it's such a diverse subject.
What is your favorite topic in mathematics?
My favorite topic? I'm very excited about prime numbers, can you tell? So I really like number theory, but I think maybe my favorite thing of all is when different bits of maths come together. So the work I did for my PhD was in number theory. It was about properties of whole numbers, but I used techniques from analysis. I used techniques from matrices. I used complex numbers. There was lots of integration, all sorts of different bits of maths coming together. And that for me is maybe my favorite thing of all, is finding ways to connect ideas. So that's not exactly a topic, but that's one of the things I find keeps me kind of hooked. Okay, I'm going to hop into the chat because people are busy asking interesting questions here. So somebody's asking about coaches to train students for Olympiads. And I guess in Nepal, you are relatively new to having these kind of opportunities like this camp now. So I hope you're saying thank you nicely to the people who are organizing this opportunity for you. So you're preparing yourself. I think if you have internet access, then there are lots of really great resources out there, some of which you can access for free online, some of which might cost money. And I know that can be a constraint sometimes. But for example, the UK Mathematics Trust has lots of materials that are readily available, as well as kind of books that you can purchase and so on. My top tip really is just keep practicing solving hard maths problems. Learning new techniques is always a good thing to do, but then you have to be able to use them, and you have to be able to use them in a setting where you're not quite sure which technique to use. And my experience is that the only way to get good at mathematical problem solving is to practice solving problems. And it does work. I promise, by practicing solving mathematical problems, you get better. So I guess your challenge is to find problems at the right level. If you look at a problem and know how to do it, you're not going to learn anything from doing that. If you look at a problem that's too hard, that might not be so helpful. So it's finding problems that are just a little bit too hard, but within reach. And the more you can find, the better. And we've got resources from Oxford, for example. We have an online maths club. If you search online for Oxford Online Maths Club, you'll find lots of videos of previous sessions that you can watch. There are lots of new ideas there and so on. So I am so unbelievably old that when I was your age, we barely had internet access or didn't have internet access, but definitely there was no YouTube. My internet connection could only just about send an email. It definitely wasn't streaming videos and doing Zoom calls. There's now loads of stuff online for you to be able to access. But mostly I encourage you to practice solving problems and help each other, compare notes on problems, talk to each other. I know Olympiads are competitions, but I think outside of the competition where it would be cheating, collaborating and helping each other can be really good, because maybe somebody has a different idea from you on how to solve a problem. Maybe you can solve it in several ways. And sometimes that can be a really useful experience for kind of exchanging ideas as well. Okay, I'm going to keep going here. Do I like reading novels or storybooks? Yeah, definitely. I read lots of crime novels. I love reading maths books, but I don't want to read a maths book when I'm going to sleep, because then I think about maths. So reading a maths book in bed is, in my experience, a bad idea. Reading a detective story is a good idea. Polymath, yeah. So the polymath projects, I think they are interesting, and you can have a look online. So if you can find the post where Tim Gowers on his blog, I think it was in 2009, asked, is massively collaborative mathematics possible? He kind of asks these questions and sets out his vision for polymath. So there are some ground rules for polymath of, you know, what are the rules for who gets involved? One of the important things to decide early on was, if a polymath project manages to solve a problem and we want to publish our work, whose name goes on it? And the first problem that they tried working on, that Tim Gowers proposed using this polymath project, is a problem called the density Hales-Jewett problem, which was a well-known problem in that particular area of research that hadn't been solved. And I think to everybody's surprise, polymath managed to solve the density Hales-Jewett conjecture. So that was a kind of triumph for polymath after a few weeks. The first project solved their problem. And they published their paper under a pseudonym. So the name of the author on the paper is DHJ Polymath. So like the initials of the person were DHJ, but that stands for density Hales-Jewett. And since then, problems have been published under that name. But if you click through, there will then be a link to a web page where it lists all of the different people who made contributions. They might have been big contributions, they might be small contributions, it might be one idea, it might be helping to organize the ideas so that they get communicated clearly. There are lots of ways to contribute to a mathematical project like that. I think one of the reasons that bounded gaps between primes worked so well collaboratively was that part of the work was theoretical, really understanding the maths in detail, and that was quite sophisticated. You had to learn quite a lot of maths to do that. Part of the work was getting a computer to do certain calculations quite efficiently, and you had to know enough about kind of computer coding to do that. And those groups of people don't necessarily overlap, but by bringing them together, the theoretical people could say, well, if we knew the answer to this computer problem, we could do this. And the computing problem, people could say, well, here's some data. If you can sort out the theory, then we can do this. And it was really efficient to bring those groups together, which might not have happened otherwise. So yeah, I encourage you to search online for information about polymath projects. How do I find maths? Is it interesting, easy, hard? I don't find easy problems so exciting. I mean, sometimes it's nice to look at a problem and think, oh, I know how to do that, and I'll work through and I'll turn the handle on my kind of metaphorical machine and I'll get the answer. Sometimes that's kind of comforting, I guess, like comfort food. But I like problems that I have to stop and think about for a bit. And I like problems that I can discuss with my students and they can have different ideas on how to solve them and so on. So for me, one of the things I like about maths is that I find it challenging. And when I stop finding a bit of maths challenging, that means it's time to go on and find another bit to keep thinking about. What is the purpose of learning maths? If hypothetically there's a tool that solves maths problems, do I think maths should still be taught in schools? Wow, these are deep questions you're asking. I think that as a learner, it's helpful to learn maths because I think the skills that we can learn by going through the process of learning maths are themselves valuable. Also, the knowledge that we gain about maths can be useful. So when I think about what my students do, most of my students graduate when they're 21 or 22. And then some of them stay in studying maths to a more advanced level, or they move to using their maths to study other subjects in kind of applications. Lots of them go and get jobs in different ways. And sometimes the jobs that they do really use the maths that they've learned. But more often, the jobs that they go on to do, it's not that they know lots about number theory. It's not that they know lots about Galois theory. It's not that they know lots about partial differential equations. Their job they're doing don't need that. What they do need are people who are numerate, who are confident with numbers, who can analyze data, who can maybe code for a computer, who can think logically, who can reason clearly and carefully, kind of logical order, who can explain complicated arguments clearly. And those are all skills that people learn by studying mathematics. So even though I can ask my computer to solve some maths problems, the process of a human learning to do those, I think, is still valuable. And also, we need people to tell the computers how to solve the problems. And learning maths is a really good way of doing that. So I have students who go into machine learning, into artificial intelligence, those kind of subjects. Studying mathematics, statistics, those kind of things is fantastic preparation for going on and working in those kind of sectors as well. So I don't think mathematicians are going to be made redundant by kind of robots or machines or computers just yet. Why is 1729 called a magical number? Yeah, it's in my Twitter handle. And I picked it because it has two interesting maths connections. So let me tell you about these. there are two very famous mathematicians in history called Hardy and Ramanujan. Have you heard of these people? Maybe, maybe not. So Hardy was a British mathematician. Ramanujan grew up in India. He moved to the UK at Hardy's invitation to work together. And the climate did not suit Ramanujan, and he became very unwell and was in hospital. And his great friend Hardy went to see him in hospital. And Hardy was a great mathematician and terrible at small talk. So he didn't quite know what to say to his friend in hospital. So he said, oh, the taxi I got from the station to the hospital, the taxi number was 1729. I hope that's not a bad omen for our maths conversations today. It doesn't seem like a very interesting number. And the story is that, quick as a flash, Ramanujan replied, no, Hardy, it is an interesting number. It's the smallest number that can be written as the sum of two cubes in two different ways. So now you can go and think about how to write 1729 as a sum of two cubes in two different ways. It's also the third Carmichael number, and Carmichael numbers are very interesting in number theory. So it seemed like a good number for me to pick for my Twitter handle. Since I talked about, oh, sorry, I'm fighting my laptop. Since I talked about bits binding together in maths, how amused was I when I first learned Euler's identity, connecting exponentials, complex numbers, and trigonometry. Yeah, it's a fantastic identity, isn't it? So I get to teach students now that e to the I theta is cos theta plus I sine theta. And I was very excited when I first learned about this. It's hard to describe how fundamental it is in the maths that I do. I used this all the time in my PhD thesis, the fact that e to the 2 pi I is 1, for example, or e to the pi I is -1. This is kind of literally underpins a whole bunch of what I was doing. So yeah, I'm a big fan. I hope you like it too. Okay, you are asking questions faster than I'm answering them. I think that's a sign that I'm talking too much. Who inspired me to be a mathematician, and how do I use maths in my daily life? I don't think I was inspired by any one person. I was lucky that I had some encouraging maths teachers when I was at school. I also read some books. I remember watching a TV documentary about Fermat's last theorem when I was maybe only slightly younger than you are now, about Andrew Wild's proving Fermat's last theorem. I watched that in the 1990s. That was inspiring. I think I was inspired by maths, and lucky that there were people around me who supported me and encouraged me when I said, I think I'd like to keep studying maths further. How do I use maths in my daily life? Well, mostly in my job, I guess, kind of all the time. Yeah, I'm using maths all the time. What's the sum to the nth term of the cube roots of the first n natural numbers? That sounds like a really interesting question, and I don't think I know an answer off the top of my head, I'm afraid. So if you come up with an answer to that one, you can let me know. Have I had any failure in maths field, and did I think of quitting it? And what's my feedback for people getting discouraged with failure? I mean, I failed to solve many maths problems. That's normal for mathematicians. Every mathematician has a whole bunch of experiences of not solving maths problems. And yeah, I wasn't always sure that I was going to get a job in this area. So as I came towards the end of my PhD, I was applying for lots of jobs, getting rejected for lots of jobs, lots of rejections for lots of jobs. I felt like I needed to pursue what I thought was important and what was the right job for me. And I'm very fortunate that it worked out. I feel like I had luck on my side there as well. If I decided to go and do something different, if I hadn't stayed working in a university doing maths, if I'd gone to do something else, I don't think that would have been failure. I have students who do a maths degree and then go and do something else, and I am as proud of them as I am of the students who decide to stay studying mathematics further or working in mathematics. As a society, we need people to work in lots of different sectors. We need mathematicians to work in lots of different sectors. So If you are getting discouraged by solving a problem, then my advice is to park that problem, put it to one side for a bit, go and do something else, try a different problem, go for a walk. I find going for a walk is a really good way of not thinking too hard about a maths problem and letting my subconscious work on it. And if you think, oh, actually, I've enjoyed maths so far, but I think I've done enough maths and it's time for me to do something else, I don't think that's failure at all. Don't be discouraged. Find something that you find exciting and worthwhile to do and go for it. Maths is a difficult subject and many students struggle with it. How do we deal with that? Yeah, so I try very hard to support my students because maths is hard, you're right. And we all have times of struggling with it. And we all have times of doubting, am I good enough at this to be able to do it? So yeah, find people around you who can support you in those moments. I believe in my students, I can support them. Maybe the reason they're struggling is that there's a specific topic that they just haven't learned and I can lend them a book or help them out. Maybe it's more about the psychology. Maybe they need to try to set aside the voice casting doubt and just try experimenting with some ideas. So yeah, I think there are lots of different ways. It depends exactly why students might be struggling. If you feel like you're struggling, then ask for support from the people around you. Be upfront about how you're feeling about it. Have I ever visited Nepal? No, sadly, I have not. I'm very happy to be virtually with you today, but it's not quite as exciting as visiting in real life. I have various friends who have visited Nepal, but I've never been. So maybe one day, maybe. How do I stop procrastination while solving maths problems? Yeah, that's a great question. I guess it depends what your deadline is. If this is like, I need to hand in some work in 2 hours time and I need to do these, maybe you have to try to persuade yourself to just focus for a couple of hours. If it's a long problem, if it's a problem that you're expecting to spend time on, days, weeks, months, years, go for a walk, do something else. If I'm stuck on something, maybe I'll try to do some admin or do the washing up or do something to distract my mind. I find my subconscious is sometimes a better mathematician than my conscious me. So I have to spend time consciously working on a problem and trying out ideas on a piece of paper because I need to immerse myself in the problem. I need to really live inside the problem. I need it to kind of inhabit my space. But sometimes I go to bed and then I wake up in the morning and I've got an idea from nowhere, or I go for a walk around the valley where I live and I come home and I think, oh, well, maybe I could try this. And so sometimes walking away, literally or metaphorically, I think can be helpful, but it does depend on your deadline. How are we doing on time? Do you need to finish or do you want me to keep answering questions?
You can go on if it's viable for you, but we can stop after 2-3 questions. You can take
Can I ask a question?
and stop it.
Okay, let's see whether we can squeeze in a couple more. I don't have to be anywhere right now, but I am going to have to go soon, and I'm sure you will have to be somewhere as well. So yes, sorry, I didn't spot who it was who asked a question on the mic, but please do.
Yeah, I wanted to ask that, what is your motivation to stay focused?
Sorry, say that again.
What is your motivation to stay focused?
What is my motivation to stay focused? I'm really curious about maths, and I think curiosity is a good motivation. One reason for wanting to ask a question is that somebody has given you the problem and told you they need you to work on it. Your teacher gives you a problem or something. But I think the best motivation is if you are curious to know the answer yourself, because then you have a reason within you to want to answer it. And sometimes when I was studying, people would give me questions and I was not so excited about them. So sometimes I just did them because I was told to. But often I found, as I started thinking about the problem, I kind of got to thinking, oh, actually, yeah, that's kind of interesting. This is surprising. This isn't what I expected. I quite like to know the answer to this. So yeah, curiosity, I think, is a powerful motivator. Do I think mathematical truths would exist if there were no people to think about them? Yes, I absolutely do. So I guess I might call this a Platonic worldview following Plato. I believe that there are such things as perfect Euclidean triangles. I believe that angles would add up to 180 degrees, even if nobody thought about that. That's a philosophical question. That's my personal philosophical view. You're allowed to have a different philosophical view. Do we need more creators like Grant Sanderson from 3 Blue 1 Brown? Yeah, absolutely. I think finding innovative ways and creative ways to communicate mathematical ideas is a fantastic thing to do. I try to do it a little bit myself. I think inspiring other people to think about maths is a really great thing to do. I think it's great that we have people in universities doing research on maths, pure applied statistics, all sorts of different things. I think it's great that we have people teaching maths in school, in universities. I think it's great we have people using maths in lots of different industries to help society and to help other people. I think it's great that we have people who are inspiring people to take up maths. And I hope I can sort of do a little bit in some of those kind of areas. I think, sorry, go on, yes.
May I ask you a question?
Of course.
In your opinion, what do you think mathematics really means to you?
Sorry, what does mathematics?
In your opinion, what do you think mathematics really means to you?
What does mathematics mean to me? I just find it fascinating, I guess. So I think it's fascinating that we can make these ideas, that we can understand this mathematical universe that I think is there even if we didn't understand it. And I think it's fascinating that by understanding that, we can then use that mathematical learning in so many different fields, as well as being kind of curious about mathematics in itself. So I guess we should probably stop because you've maybe got maths problems to work on, or maybe your families need you to go and do something, or go and have some food or something. So I guess I would like to say thank you for inviting me to join you today. I hope that you enjoy the rest of your camp. I hope that you stay excited about mathematics. It's completely normal to feel not quite so excited about mathematics always, but keep being curious, keep inspiring each other. I think it's great that you are building a community through having this camp now. I'm sorry I didn't manage to answer all of your questions. I tried to answer as many of them as I could. And good luck, all of you, with your future mathematical adventures.
Thank you, ma'am. It's been a pleasure to have you. And I think all the students have learned a lot from you. And like from the queries you answered, I think they must be motivated in the future too. So yep, like I think it's time for you also for your other work. So I think we can end this meeting. And I'm very thankful for you too. So if other students want to like give a thank you message to ma'am, you can do it right now in 1 minute, and we can end it.
Thanks, everybody. Enjoy the rest of your day.
Thank you very much.
Thank you very much.
Thank you, ma'am.
Thank you very much, ma'am.
Thank you, ma'am. It was nice to have you here.
It's great to see so many keen young mathematicians.
Thank you so much for giving your precious time to us.
Thank you, ma'am. Loved your words.
So I think the host can end it, or I think we can all leave the meeting. I think the host has some technical issues, so I think we can all leave the meeting. So it's been a nice 1.5 hours, 1 hour, 30 minutes.
Bye, everybody.
Bye, ma'am.
Bye.
Bye, ma'am.
day.